You might have used a printf statement, something like this. Tell me what it will print. A has value say percent B, and then B has value percent S, and then close the quotes and say A comma B, right? So it will print A has value whatever the value of A is, and then B has value whatever the string value of B is, right? That's a normal program. Okay? Now C will also accept programs without any, so what is this called? This is called the format specifier. The %d and %s is called the format specifier. It specifies that at this place there should be an integer, at this place there should be a string. That's why it's called a format specifier. Okay? Now, you may think the program may not execute without format specifiers. You can try it out. Actually it will run. So for example, I could say simply printf A comma B.
It won't give it'll just print.
If the value of A and B are set up front like this,
okay, yeah,
it will print them. But if the values for these two variables or any of these variables is passed at runtime by the user as input, if he passes the right values, it will be fine. But if he misuses it, there will be a problem. So that's what is called a format string attack. Right? So for example, let's just focus on B because it's a string, right? So I can put anything in a string. So let's say printf B. If I pass a regular string, say hello world or something, it will print that. But instead of hello world, let's say I pass something else. And those are the three things I want to illustrate here. Let's say I pass this as my string. Okay, %08x, %08x and so on. So you should know what are the different possibilities. You can see you have all this %d, %s and all those things, right? %d is for integers, %s is for strings. Similarly, %x reads the data from the stack. So if I say printf %x, like what I showed there, it will try to read from the stack and print the contents of the stack. Okay? If I say %s, it tries to read data from the processor's memory. We'll see an example of all these things. Then %n tries to write, once we go to the example, we'll understand that. Okay, let's start with this. If I pass something like this, right, and this is a C program that has vulnerability. Instead of printf specifying a format specifier, all I am trying to do is print RB of 1, which is accepting input from the user. So whatever the user entered input at command line, I'm printing it out. So the user entered this large huge string as the input at command line. There's a problem here. Why? Because if you pass something like this, it will retrieve the 5 parameters from the stack and print them as 8-digit padded hexadecimal numbers. So the possible output will look something like this. So each is a 32-bit address, right? So not an address, is actually 32-bit quantity. Okay. So what it does is, remember in those figures I showed you what is called a stack pointer, right? So always the stack pointer points to the active stack, the stack is currently being executed, and where it is currently in that function. For example, this is function B. So it is pointing to this memory address. So when I pass that %OX and all those stuff, it will print the I had that 5 times over there, if you remember, %OX, %X 5 times, right? So it prints the 5 memory locations starting from the stack pointer. What are the values of those memory locations? Alright? So that 4, 0, 0, 0, all those things are actually this retrieves the contents of the memory location where the stack is pointing. This retrieves the contents of the subsequent memory location. This retrieves the subsequent memory location, so on. So I put 5 times this, I can retrieve the 5 contents of the memory location starting from the stack pointer, subsequent 4 memory locations. That one and subsequent 4, so totally 5. Okay, so try it out. Just you have Ubuntu by now, right? On a virtual machine, just write a small C program like this, compile and run, write out by passing this, see what happens. The new Ubuntu's might have disabled, they may want you to put a format specifier. It depends on your compiler and all those stuff. Okay. On the other hand, if I pass something like this, okay, so this is a person 08x. Person 08 is actually to print it as what is this? 8-digit padded hexadecimal numbers for this x. Now, if I pass something like this, \x10, \x01, what this means is actually this is a 32-bit memory address. So this is to actually just print the contents of this memory address. Okay. So the contents of whatever the content of this memory address, and this you see 1001 4808. So it's a 32-bit memory address. So whatever the contents of this 32-bit memory address is, it is printed as a string. Okay. So you could read from any memory address whatever the value is, and you could print it as a string. Okay. You see what a user, as a developer, you might just think that this is okay, but an attacker could misuse it and try to pass inputs like this. So the last one. Let's say instead of this RB of 1, I have my program something like this. Printf RB of 1, and let's say I have integer I, and I have actually ampersand I. So ampersand I actually means I want to print address of I. Okay. Now for RB of 1, let's say I pass this string as input. All it is saying is 1, 2, 3, 4, 5, put it in double quotes, so each is considered as a character. Once you put things in double quotes, it's a character, right?
So repeat, it's just going to print out what it says.
It's going to print out that 1, 2, 3, 4, 5, followed by a but you see here this percentage.
It's going to go to the next line, right?
It's not backslash, it's a percentage n. You see, this is the format specifier over here.
Okay.
Once you put the percentage n, what it does is, it looks how many characters it has printed so far, right? This printf function has printed 5 characters, right? 1, 2, 3, 4, 5. What it does is it counts the number of characters it has printed and writes that count on the subsequent variable it's going to print. Say after printing this, it's going to print what? The address of I, right? RB of 1, comma, ampersand I. So after printing whatever you passed for RB of 1, you are printing the value of I, right? So what it does, if you pass this for RB of 1, you print all those 5 characters, and once you hit a %n, what it thinks is, it counts the number of characters that's printed so far, which is 5, and whatever the value of I is, it's overwritten with 5. So I maybe say some 100 or something, and you're trying to print the address of I, but with this you're overwriting what? The value of I. Right? So you're printing 5 characters here. So I's value will be overwritten. Clear? So if I want to ask a small question on this, I could give say I equals say 100 before here, and say printf RB, even without ampersand I can just say printf RB of 1 comma I. It's also okay, right? But what is the answer you should say? It will print what? Depends on what you pass for RB of 1, right? It won't print 100, isn't it? If I say I, okay, now for RB of 1, I pass what? Something like A, B, C, D, %n, what should be the output? What should be the value of I it gets printed? 4. Because it prints 4 characters followed by %n. So it counts the number of characters that have been printed 4. So I's value is overwritten with 4. So it won't be 100. So this is a small example I could ask for a format string attack. Okay, so remember those 3 ways. This is one. The other is using \x for the address thing, so you could print the contents of any address. And same thing with the stack. You could print the contents of the stack. Okay, so this is printing the contents of stack pointer followed by subsequent memory locations in the stack. Okay. All right. So that is another thing. And let's see. The last thing is called the time to check before we move to database. So there's one more C vulnerability which I want to go through, and this is actually a project 4. If someone has started project 4. It's called time of check to time of use. So let me just give an overview of it today, and we'll see that more detail next class. So make sure again to come next class. So what is this about? Let's say you log into POS, right? And you stay logged in, which means you don't log out. You have the terminal, everything as if you are logged in. And you try to say register for your courses, right? So you logged in, say, let's say you want to register for spring. Okay, so you logged in now, and you kept it logged in all the time for like several days, and then after say certain days you try to register for the course, right? What will happen? You could have logged you out after a while, right? That's a security feature. Why? If they don't log you out, right? You log in say today, and you try to register for a course say 3 months from now. If say you have not paid the fees for fall, okay, they may not have validated your account when you logged in today, right? Because when you logged in today, the fall semester is still running, so you may pay the fee sometime later. But after 3 months, if you have not still paid the fees, they should lock your account so that you should not be able to register for spring, right? But if you didn't log out from your account on your system, okay, and you are not validated for paying your fees at the time of your login, if it remembers that and lets you register for the course, there's a problem, right? Because at the time of you logged in, you are okay because your account was not locked. But when you try to register 3 months from then, if it still remembers what was the status of your account at the time of logging in, there's a problem, right? So which means there should not be appreciable time between the time it checked your access permissions or status and the time you really want to do certain things. Okay? So that's what's called time of check to time of use. There shouldn't be much time gap between the time the operating system checked whether you have the right permissions to do certain thing and time you really want to use that thing or do certain, like registering for the course. In the project, what you are trying to do is a Java program. We'll see it as a C program here. But in the project, what you will do is you have, if someone has read the project description, you will create 2 user accounts, say user A and user B. Okay? And actually, I think user A has this file. It could be any file, say readme.txt or any file. Okay? And using the chmod and all those things, you are giving, say, user B belongs to the others category. You let the others to be able to write to the file. Okay? So that's the initial setup. So now you have a file reader-writer program that will actually, I think B. You could develop it at B. At B side, you develop or write a program, which is a Java program, to read and write to a file. Okay? And you pass this readme.txt as the name of the file you want to read and write to. If user B, as others, has the read and write permission on this file, you can read the file, print all the contents and write to the file. Right? So in your program, you simulate writing, you write a line for probably the date and time of the system, and then sleep for a certain time, and again write to the file and so on. So you write, say, several lines by sleeping, and then again writing, and you sleep and then write. Okay? Because if you run without sleeping, it will just write quickly. If you write a for loop to write 10 times, the loop will run quickly and then the program will terminate. So you won't really see the effect of this. That's why I make the program to sleep after every time it writes. Okay, so the program, user B has developed a file reader writer program to open the file of user A and write to the file, because user A has given the write permission to user B. Now let's say the program has opened the file and is writing to the file line by sleeping and all those things. Now user A changes his mind and removes the write permission he has given to user B. But user B is currently writing to the file, right? Do you think, let's say user B has written 5 lines to the file, and once user A changes, do you think user B will not be able to add the next line to the file? Yeah, it will be still able to add. It will be still able to write as many lines it wants to the file before closing the file. So that's the file descriptor vulnerability. Remember sometime back we read about file descriptor vulnerability? You check for permissions only when you open the file and assign a file pointer or file descriptor to that file. What are the permissions you had, you will follow them every time you want to write or use that file. So if your file descriptor has been opened to be able to write to the file, even though the actual owner of the file has removed the permissions, you will be still able to write to the file. Okay? So now say the user B has stopped the program, which means the file is, the descriptor is closed and everything. Now he again launches the program, but user A has removed the permission to write the file now, right? So when you start the program from scratch or fresh again, you will not be able to write to the file, because now when you try to open a file descriptor to write the file, you don't have permission to write to the file. So the operating system checks only when it opens a file descriptor. Okay? And it doesn't check every time you want to really use it. So that's again time of check to time of use, because if you really want to avoid this attack, every time you want to write to the file, you want to check whether he has the right permission. But it's a trade-off, because it will delay the runtime. Every time you want to check, you want to make sure the user has the right permissions, and then only you can write to the file. There's a delay involved in it. Okay? So that's why operating systems normally do it only once and remember it, and then only the next time it's open, you try to again check. So that's the vulnerability. That's from time of check to time of use. The time you check is one time, and the time you really use it is some other time. But there shouldn't be a huge time gap, like the previous example I told on the pause thing. If you let, like for example in this case, if user B is not closing the file, he can write as many lines as he wants, right? Even if he can run the program for like 3 months without closing the file, he can write any number of lines, right? So that's the vulnerability with this. So this is from a Java context and the database context, but try to see if you can read through this. This is from Unix point of view. We'll look at this vulnerability next class. Okay? So after this it will be more easy. So these are 3 main kind of